Good evening, everyone. My name is Ved Prakash, and I am currently pursuing my MTech at IIT Patna in the Department of Computer Science. Today, I am here to demonstrate a project which I have built to understand how actually real shell like bash work internally. The shell reads a user commands, parses that command in tokens, and execute the program using Linux system calls such as fork, execvp, pipe, duck2, and waitpid, etc. It supports the pipelines, output redirection, background processes, job control, and command history, signal handling, etc. So I will show you the demonstration of this project and show you some of the important working. Also, let me first compile this program and let me first delete all these files. So our compiled file will be again compiled. Okay, here we have our compiled file, this object file. Okay, we have recompiled it by mistake. Okay, let me, this is the file cw shell which is we will run now. Let me show you some of the basic commands like list down all the directories, current working directory which is Mini Unix Shell. This is the directory where my project is running actually. CD docs, like this is the document directory. So you can see now this is in the document directory. We can go back again. These are the some of the basic commands, like some file we can create, what f.txt, this is the file. We can print something on the screen like hello using the echo command, and exit is a basic command which actually exit from this shell program. Let me again run this. Okay, so these are the basic commands which we have implemented in our project. How actually shell programs work, let me tell you something about that. Actually what our shell creates a interactive loop of this prompt cw shell. It print that prompt and wait for the user input. We as a user type some command, like maybe something we want to do some task, and our shell program actually parses that command and then understand the meaning of that command and then creates a child process for that command, and then accordingly if that process related to that command is need to be a built-in process or a executable executevp process, which is inbuilt process in the Linux to execute some of the commands like ls and like pwd. These are the commands which are already we can call using a system called execvp executevp command, which is in this library, this unix std.h library. All these functions are declared in this library and we can use them directly in our program here. Let me show you some of the other functionalities. Actually I was talking about how the shell works. So when we call this program, this our shell program creates a process which is of course the shell process. It creates a interactive loop which is in this, you can see it is an infinite loop we can say, and which waits for the user input continuously, and using that user input it actually, after that taking that user input, it parses that command. Okay, this is a parser.cpp we are using here. This is a parser, this is a parse command function. Its definition is in this parser.cpp file, and then accordingly if that program, if that command is an inbuilt command or executable command, it runs the process, child process related to that command. Let me show you some other workings. Let me first create some file. Okay, we have created these three files: test.txt, test2.txt. Okay, let me show you. If we this is the command we wrote here, echo hello everyone to this test.txt. This is the symbol we are using to differentiate in the commands that it is a redirection command. Actually, it redirects the this input to that file. By default, a shell process, a child process, any process have three file descriptor values, 0, 1 and 2, for the input outputs at the screen or terminal. By default, when we echo cllo, it will redirect, it is redirect to the screen, actually to this terminal hello, it will print this to hello. But file descriptor program actually redirect this hello everyone, this content, to this file. Actually, every file or an input output resource is identified by a file descriptor integer number. So any process have three by default uh, file descriptors, 0, 1 and 2 for the screen, for the input, std out, std in, and user input. So when we call this, our file descriptor program actually redirects the content to this file test.txt. Let me show you here. Okay, so when we read any file like this fd equal to this, open out this file, it will take the file descriptor related to that file. Maybe some of the file descriptor value assigned to this is like maybe 4, and that file descriptor value will be replaced with the std out file number here by the w function, and then this will work, echo will work here out, and then we will close that file. Now I will show you how the pipelines work actually. Before that, I want to show you, and this is a command test2.txt used to, okay, we have wrote a wrong command actually. It will print directly this content to the file, and test2.txt is right now empty, so it will not print anything. Let me write a correct command. Test2.txt, and then here it will print this. So you can concatenate two processes, like we have created this hello everyone and hello everyone. If we want to change the content of this test2 dot, and then print again this, this time let's say we want to sort the output. This is hello everyone and I am with. So actually test2 dot text contains what I am with, and test1 dot contains this. If we don't use this sort, let's see, it will print without sorting. It is like I am hello, how are you is above the hello everyone. So this is due to the pipelines we have implemented in our program. Pipelines are basically used to communication between the two processes in the shell. So this cat is a process, it is a child process, and it will return some output which is the content of these two files, test2 and test.txt in the concatenated, and sort will be the another process which takes that output of this process through the pipe, through a pipe. It is a logical pipe we have created through with our program, and it will sort that in the order. These are the two files I have created, file.out. Okay, now we will try to list down the files and then grab only the files which contains this pattern txt. These are the files 3.txt and test.txt and test2.txt. This is the 3.txt file, and these are the files we have worked. This is the same concept of pipeline. ls is a process, grep is another process. It takes the output of this ls through the pipeline to the process grep, and then match the pattern with the output of this ls, and which have this pattern text, it will show that as output. We can get them in sorted order also, but let me show you in different way. Like, first I will change the content of this file test2.txt. Hello, this will, how are you? Now I will write here I will write something for the sorted version. This is without something. Let me save this. So we have back to the shell, and here this is the content we have changed, and now I will show you how we can actually use multiple pipes in the shell. Grep will be used to get the pattern having, let me do this here, so that I and a will be go up above, and so, and sort it. You can say a hello and hi, hello everyone, and hello I am Ved will be like here. So this is like that. Okay, we have not saved that content earlier, so if we can take that data in another file also. This is result.txt file is created here, and it will contain all these in the sorted order. Let me print it here. So this is the data printed here. This is a space, so that it is sorted here in this order. And after that, let me show you that it will sort it properly. Now it is containing the exact sorted order of this file. Okay, so now we can understand this is the multiple pipes implemented in this shell, and now we will demonstrate you how the background processes work. Sleep 47. Okay. See, here we have not written the background representation of this process sleep, so we should wait for the completion of this process for 40. It will take 40 seconds, and after that we will be able to run another commands. If we write commands right now, it will not work. It will work only after the sleep 40. It actually, these sleep commands actually stop our parent process uh, from working, and after the execution of these sleep 40 process, which are actually running in the foreground, not the background, so our shell got blocked. After these 40 seconds, this process has been completed, and we can see these two commands, ls lsv command actually executed 2 times. These are child processes created at that time, but our shell gets blocked due to this sleep. If we use the background representation of any process, like now, it will not block our shell. We can work in our shell as we want. You can see here, and you can see this process is running now. Even let me show you many sleep processes, how it works. These are many sleep processes. These are the 3 sleep processes we have created. This is 40 and this is 50, and this is the 10 seconds only, so it is probably completed its execution and gone out. So let me show you another concept. Let me show you about the job control. Actually, when we created a process in the background and it runs in the process in the background, it runs in the background, we can take out that background process to the foreground. Let me show you how. This is the track of our all the processes which are running in the background currently, and we can take any process in the, let me show you process 1. It came out, and again let me fifth process, because the fifth process have not completed its execution and it came to the foreground. We have to wait for this process to complete its execution. After the execution is being completed, we can use our shell again, because this sleep process blocks our shell. Actually, job controls are working. Let me show you how the signal handling works in this program. We have not written any background representation, so it will block our shell for the 100 second. But if we press Ctrl plus C, it actually does not move us out from the whole shell program, but only the current process, current child process, and we can use our shell again, like history. This program history is a built-in program. So what are the built-ins? I think I have told them earlier. Built-ins are the processes which we need to implement in our program externally, because for these we don't have any functions like executevp etc., because these processes need to change the execution of the parent process, because history needs to track the how many childs have been created till now, and what are the commands we have given till now. So it needs to manipulate the execution thread of the parent process. So that's why we need to implement these in the built-ins. So this is a built-ins .cpp. Actually, jobs is a built-in command. cd is a built-in command. Cd is a built-in command, and change that directory, because if we do not use this in the built-in and we try to use the executevp, it will not work, because it will change the directory for the child process only. But we will, when the child process get completed and we came back to the parent process, the directory will not be changed in real. So that's why we need to implement this in the built-ins. So we can exit now from this program. Let me show you how the zombie processes work. Before that, zombie processes are the background processes. Sometimes the background processes can create the zombie processes. Zombie processes are those processes which have completed their execution, but our parent process did not call the wait function for them, and because of that, their ID in the process table remains even after the execution, but it should not be there because they have completed their execution. Their process ID should not exist in that table. So let me show you this, how the zombie processes are handled in this program, because they should not be there. uh, Let me give some bigger number. Oh, it got so many. Oh, sorry. It will, it is, these are the processes, three processes which are running currently, sleep 50, sleep 60, and these both are the sleep processes right now. And one of the processes which was having 30 sleep timing, 30, has been completed probably his execution, so it is not showing here. And it is not even in the zombie process, because there is a this there is this is what, this is a representation. What type of process is this? S for sleep process and R for running process. And in this way, for example, we can show you, like, find is a process. This, this process is running and it finds all this in that. Let me show you this, how this representation is looks like. So it will find in these, and if I print the process, oh, I can't do that because my shell is trying to take my input, but instantly this process, which is this find, types its output here, so that's why I cannot do that. Even my shell did not block due to this process, but I cannot show you that because it is kind of, you can say, a conflict between this process and what I am typing here. So because I am able to type, but due to this output I cannot do that, because at the same time two processes are trying to use the terminal. That's why this is happening. There is no process in the sleep right now, you can say, and even in the zombie there is no process. If I can show you how this exit is a built-in. Now we will exit from this shell, and this is how we have exit from our shell program. And let me show you how the folder structure actually works. This is the document folder for this. In this I have wrote some of the operating system concepts and working of the shell programming tree, how this works. It reads a command and then parse that command, then create a process, child process, and execute that child process. And till then, if, when executing child process is executing its program, parent process wait for the completion, and then it shows us the prompt again. This is exactly how the shell works. So this is a wait call which is used to wait for the child process execution in the parent process program. This is how, this is the folder. These are two files we have created for the test purpose, and this is the include directory. In these we have these header files, uh, here built-ins.cpp. Here we are defining all the functions we have declared there, void show history, void add history, etc. You can see here again, these are show history, add history. This way, these are the other functions we have used. And executor.cpp, this is actually responsible for the execution of our program, our child processes, and even for the parent process also. Here, let me show you where the child process program is. If the process id equals to 0, it is representation of the child process execution. So here the child process executes its program, and this is we are using for the signal handling like control plus c and control plus d, etc. Here this is we are using here for the output redirection purpose. This dub2 and these they actually reads the file and close the file in this way. uh, dub2 actually redirect the file descriptor value with this std in, and here it is replacing that fd value with the std out, because here we want to read the input, here we want to write the input to the file, this std file number. Okay, so open, when we open any file, we get some file descriptor integer value, and that file descriptor integer value will be replaced with this std out, and then it is closed. And because of this replacement, we will be able to perform the task like echo hello to some file. We can say this file. Oh, this is written in this. Because of this, because the file descriptor actually replaces that value, dub2 actually replaces that value with std out, which is by default file descriptor value, which is 2 for the processes. This is how this project is working. Thank you.